So if you are following along in the book, we are probably somewhere in the middle of chapter 4 or module 4, moving into module 5. And I was going to talk a little bit more about numeric data types today from chapter 4. We've really, for the last class or two, been in 3, 4, and 5. And there's a lot of fundamentals here. There's a lot of interesting things that we can do, but we can only go so far until we get into chapter 6 and onward, where we can start doing conditional statements, if statements, get into some of the logic that our programs can implement, and later into repetition, so we can do loops and things like that. That's when the programs get really interesting. So I don't want you to be lulled into complacency if you think that so far the assignments have been a little easy, because again, for people that are taking this class that have never programmed before, it's important to get the how you manage your files. It's important to understand the flowcharts and pseudocode and the role that they play, and not just jumping in and start coding, but the fact that in the real world, most software developers that are professionals out there, they do spend some time designing, and there are entire jobs where their title is architect, and that's all they do, is they live in the world of drawing boxes and things. If you take the system analysis and design class, you'll get into that a lot more, the various ways that designs and architectures are communicated between software developers and from architects down to software developers. And it gets a lot more advanced there than we're getting into. So here, the main point is simply to understand that there is a design phase into it. It's not just sit down and a couple hours later you've cranked out, Halo, right? A lot goes into it, especially when most of our stuff is by definition individual assignments. And in the real world, if you're working at a company, you're going to be working in a team. There are some projects that I've worked on where they have 100 software developers divided up into different groups, and they're all assigned different parts of the project, and they're working on their own bit, and then it all gets integrated together, and it's a big commotion trying to test everybody's software at once, to more modern approaches where you have smaller, maybe 6 or 8 developers on a team, and they start small on something that works, and in an agile, nimble way, they add features week by week by week until they have something that the boss comes in and says, okay, we're ready to ship this, let's start making money off of it, type of thing. So that's the main thing. One of the things that I wanted to point out is there seems to be some confusion with shapes a little bit. And I want to point out that, if you create a flow chart and it's just, a bunch of circles, I kind of said I would be lenient and let people turn stuff in if you drew it on a napkin and took a picture of it and submitted that. Well, that's assuming that everything's correct. If you say start and then you do something and then you input and then you do something else and then you output and then end, right? This is not a flow chart, okay? The shapes are significant. They mean something. They convey something about the code that's going to come later. That's the reason why it's valuable, although not required, to use a tool like Flowgorithm or Raptor or any number of these utilities out there that exist that help you walk you through and have a bunch of cool features about them once you do put it in there. But an oval is strictly for start and end, or begin and end. If we're declaring something or doing something initially to initialize our variables, that's a rectangle. Those are usually do type operations. An input is always a parallelogram. You know, if we're going to go get something from the user later, when we're, you know, talking about opening up files and reading data from files or databases, those operations would also be in a parallelogram because they're input statements to our algorithm. You know, then we might have some more calculations. Again, that goes into a rectangle. Yeah.
For the last assignment, you just had to turn in Python.
Correct. Yeah, and you'll see I'm starting to relax that. I don't want to drive it into the ground and make you do pseudocode over and over and over again for seemingly easy algorithms as we wind down through chapters 3, 4, and 5. But that's kind of my point, is when we get to the later chapters and we're starting to, I mean, we're going to revisit flowcharts and pseudocode when we get to the next unit on conditionals, where we have if statements, and then later when we have for statements and while statements. Those are all going to have to be flowcharted, and so you understand what the design is in a flowchart. You know, if I have an if statement, it's going to be a diamond. You know, and we're going to have multiple paths that come out of it, right? If yes or no, then we go different directions. We may do some other input, some other calculations. We may do some more inputs, you know, whatever. And then outputs are also parallelograms. So finally, at the end, we produce our results, and fini, we get to the end. Now, I don't get picky on if you say begin instead of start, or you say stop instead of end. I don't care. The meaning is conveyed. But, you know, this thing over here on the right or on the left, yeah, that's not a flow chart. You know, the thing on the right, it doesn't have to be pretty to convey the point, but, you know, you got to give me something here. You got to show me that you got the point of it. Make sense? Any questions about shapes? I don't care what color they are. You know, Flowgorithm makes input a different color than output. Yeah, I don't care. That doesn't convey anything to me. But you got to do it right. You know, generally you start at the top and you flow to the bottom. That's pretty much a convention. You know, at this point, that's all you need to be worried about. Like I said, we'll talk more about flowcharts when we get to if statements, and how we do the variations of an if statement, if else, and all that, and how we do those in flowcharts. We'll talk about that. So that's one of the points that I wanted to make tonight. Let me see what was next on my list. I enjoyed, you know, the Mad Libs project. I ran through and graded those, and it was really interesting seeing what people came up with. Thanks for the creativity that you guys showed there. It was really interesting seeing those. I thought that was a fun project, and everybody seemed to get into it and do a pretty good job of it. So thanks. The book goes into talking about the breadth of all of the different data types. I would pay particular attention to how the floating point numbers are represented in memory, because that's kind of interesting. So let's see, how can I just bring this up? So we'll go back to W3 Schools again for their list of the Python data types that are supported. And I want to make the point that no matter what language we're talking about, if we go to C# or we go to Java or we go to C++, you're going to see similarities and you're going to see differences. So they'll pretty much all have a string data type of some type. They'll have integers of various types, and they'll have decimal, you know, floating point values of different types. And then it gets weirder from there. But one of the things to keep in mind is that these are different sizes in memory. All of this stuff is an overlay over what the computer is actually doing. You know, we're abstracting these data types. We made them up, in other words. In a computer, you just have bytes of memory, and the processor performs operations on those bytes of memory. So when we talk about an integer, does anybody remember from the book in Python how many bytes an integer is?
16 per character.
16 per
Character.
No, okay. I'll give you a break. It's kind of a trick question because, and it goes to my point about how we're abstracting this, we're making it all up. Technically in Python, an integer can be unbounded in size. It's however big your hardware underneath it supports it. So we have to ask, when we're running Python on this particular computer with this implementation of the compiler, in this scenario, how big is an int? Well, it's typically going to correspond to the word size on the computer. Well, what's a word? And that goes to, so you have bytes, you have words, which is often 2 bytes. You have double words, which are 4 bytes. And like I said, from the early days, that was the name they gave to them. If you were dealing with a 1 byte value, you can only store the numbers 0 through 255 in a 1 byte value. It's got 8 bits. If you just start counting all the possible combinations of ones and zeros that you can put in 8 bits, there are 256 of them, 0 through 255. Okay, so they needed to store numbers that were bigger than that. So they said, let's see if we can make a 2 byte value and make our processor support that. And so they did. You know, the early computers that I dealt with were 8-bit computers so that they could do small arithmetic. And it was hard for them to do bigger arithmetic. Well, the newer computers came out and they had 2 byte words and they could do 2 byte arithmetic up to 65,535, I believe, if my memory is correct. 4 bytes goes up to like 4 million and something, or 4 billion. So each amount of memory that you concatenate together, you can store more combinations of ones and zeros so that the size of the number is bigger. For a while during my career, the word size on most modern computers has been 4 bytes. But now, I mean, it wasn't too long ago, we started getting 64-bit words. So instead of 32, we had twice as big of words. One of the reasons why this is important is the speed of your processor. So in the early days, when you had 8-bit computers, if you wanted to do 2 byte arithmetic, you had to do a whole bunch of 8-bit operations that pretended to us, the end user, like it was doing big arithmetic, but it was manipulating these small bytes of data to make that transparent to us. But it was slower. If you're doing 2 byte arithmetic versus 1 byte arithmetic, it was slower. Okay. Go to now where we've got 64-bit words on modern computers. The math is really, really fast in 64 bits. I can do incredible amounts of arithmetic with very large numbers. And that's a good thing because a lot of our games, they want to do really fast integer math and the processor lets them do it, or the processor on the graphics card lets them do that. So it's a great time to be alive if you're a programmer or a gamer, right? You can do a lot of stuff really fast. So why would we ever want to go back and do 32-bit arithmetic? Why would I want to have a 4 byte value if my processor is so fast at doing 64-bit arithmetic? And the answer is kind of like, yeah, that's a good question. Why would I? You know, I declare an int, and if it's 64 bits and I can store gigantic numbers and do math on them really fast at the native speed of the processor, why wouldn't I? And so we don't think a lot nowadays like we did in the past about trying to be conservative with the size of our variables. We just have a blank check and we go out there and declare an int, and it can support huge numbers and do really fast arithmetic, and life's good. So I'm pointing this out just because underneath all this, your computer doesn't just magically wake up with an integer data type or a float data type. We have to make it support those things. And, you know, to some extent, it's less important, but, you know, your beginning programming students, it's good to start off with a good foundation and understand that kind of stuff. You know, we had to start all over when we created phones. You know, when we started making smartphones, they started off with really primitive processors, and they had to build up I mean, I just got this new phone, and so far I've only had it a couple of days, and I'm just amazed at it. For one thing, I mean, just has nothing to do with the processor or the word size or anything like that, but the battery on this sucker, my other battery, I was having a hard time making it to lunchtime without my battery being dead and having to, you know, my life was lived within 6 feet of a plug-in, right, to keep my battery charging. I've been using this one for over a day now, and it says I've still got a day left on the battery. So, you know, 2.5 days of battery on this thing, and I haven't even thought about charging it yet. That's pretty cool. But, you know, going back to the processing power and the way the data is represented internally, the cell phones are now catching up with regular computers. And now it's like, well, what's the difference? Somebody in one of my classes has basically it's a PC this size, and it has the little buttons attached to the sides of it where you can use it like a game controller. It's becoming, you know, pretty ubiquitous to have very powerful, very small computers anymore. One of these days, you know, when you guys are sitting up here and you're teaching the next generation of programmers, because I'm retired someplace, you're not going to have these big boxes sitting here. People might just be sitting here in front of a phone, you know, hooked to a monitor. One of the fun things that I like to do, mainly when I go home to my parents' house, is I'll take over their television in their living room and play them a YouTube video that I think is cool because I can. You know, all of the monitors now, or TVs nowadays, they have WiDi, or basically it's HDMI over Wi-Fi. It's just built in. And so as long as you have some kind of a device that can broadcast over Wi-Fi, then you can take over the TV and paste your image up there on your screen. So that's kind of fun. So, hey, one of these days that may be all we have is handheld, very powerful supercomputers. I saw somebody, you know, when I was early in my career, they had supercomputers called Crays, and that was what the military and advanced computer scientists would use to do all their calculations and things. And I saw somebody was comparing the latest iPhone to the original Cray. So, yeah, it's a great time to be alive if you're in software and hardware. Okay, so it's a little bit academic. Main point is I just want you to realize that all these data types do have a size. They are represented in memory. And there's a couple of things in module 4, I believe, that you should watch. There's like an IEEE standard for how to represent floating point arithmetic. And, you know, sort of the genesis for that was early on, different people started trying to implement floating point arithmetic, you know, with decimals different ways. And so the IEEE kind of got a bunch of people together and said, well, which one of these ways is the best? And everybody just said, okay, fine, I'll give up mine and I'll do it the way everybody else is doing. And they just created a standard. So just the main point there is there used to be a whole bunch of different ways of doing it. Now everybody has settled on one. And when I say now, I mean, you know, 15, 20 years ago, they settled on one way of doing it. And so it's good to understand how that's represented. There's a part of the book goes into it. And then I posted a YouTube video in there in module 4 that kind of shows you how to convert from, you know, just writing down a decimal number into the binary representation of that in memory, and then from that representation back to the decimal number. It's only like a few minutes long, but it's interesting to see how that operation happens. So I would watch that and just have that floating around as trivia in the back of your mind at this point. What else? Oh yeah, this is interesting. Complex. So does anybody remember from your math classes what complex numbers are? And kind of, it's like imaginary numbers. Do you remember that? So they have this thing. Oh, another thing I wanted to point out to you. Sometimes people get a kick out of this. Did you know there's a cool equation editor built into Word? You know, like if you're typing stuff like X, come on, Word, where are you? Work for me this time? Either my keyboard died or this isn't work or something. There we go. So if I've got a word here and I type X equals 4 plus 5, 5 by 3, you know, it doesn't look that pretty. But I can turn on this equation editor by hitting the Alt equals sign and go X equals 4 divided by 5 plus Z. You know, it looks really pretty. So yeah, that's kind of cool. I don't remember where I was going with that. What was I talking about? Oh, complex. Yeah, so it's kind of funky. When I learned about this the first time, I'm like, why would this even occur to somebody to define something like this? But you have equations like x squared plus 1 equals 0. Okay, if you were told, okay, I need you to solve this for x, you'd say, well, let's put 1 on the other side. And we get this equation. But unfortunately, no matter what we use for x, nothing is ever going to equal -1, right? And so somebody said, well, what if there was a solution to that? And that's where it's like, why? Why would anybody think we need a solution to that? But that's where imaginary numbers come in, because they say, let's pretend that there's this number I. And if I multiply I times itself, I get -1. And that's why they call it imaginary, because there is no such number. But if we just imagine that there is, and I times I equals -1, well, now we can solve this. Because now x equals I, basically. So anyway, but that's what imaginary numbers are, and you can Google that and, you know, satisfy your curiosity further to your heart's content. But it's been a long time since I cracked a math book, so that's about as far as I can go. Anyway, so there's a data type here in Python that supports complex numbers. It has the regular integer part or number part and the imaginary part. You know, so you can say things like 3 plus 4i as an expression in Python. What does that help you do? I don't know. Yeah.
Is that ever used practically?
Yeah, I haven't ever, but if you're writing theoretical problems where you need to do that kind of math, maybe you can write programs that automatically
It's about office.
solve, not, honestly, my guess from my perspective, I've never used it in my career for sure, but nor in any of my PhD research up to that point. No, I'd never used it. But it's an interesting exercise because if you can implement floating point arithmetic in a computer language on top of bits and bytes, why can't you create a complex number system on top of the bits and bytes? And that's what somebody did. So if for no other reason, I mean, there's classes that people take called compiler construction, where you sit down and you actually learn how to build a compiler like the Python compiler. So you have to invent a language or take a language that somebody else invented and add features to it. Maybe it started out as just an exercise that they gave them in class. Hey, there's these imaginary numbers, go read up about them and then add them to your compiler. I don't know, but no, practically I've never really used those.
And how many CPUs use that? So it's a manufacturer code. Like when it gets into really complex coding, is there any real processors that can take that input?
No,
Outputs to it?
no, not natively. I think it's all an addition in the compiler. It uses floating point math to implement the complex, the imaginary numbers math. Just like in the old days, we used integer math plus a bunch of stuff to implement the floating point math.
Well, but that influenced processing.
It did, because they did implement floating point units into the processors and into the graphics processors and things. You are absolutely correct. But I don't think anybody has implemented the complex part in there. But again, I think just because it's not practical, I mean, it's not something that you're going to use.
Well, it hasn't really been supported until SD drives really started to more prevalent with their memory backup.
Yeah, well, most games use the floating point unit extensively, so. You know, the floating point, yes, that's very practical. But the complex math with the imaginary numbers and stuff like that, other than just learning how math works. And there are, I think, some mathematical problems that rely on that as a basis for solving those. I just don't remember what any of them are. Anyway, so we've got that. A spoiler alert, when you start reading the chapter 5 on the strings, the main thing to remember about strings is that it's just a bunch of bytes. And you know, the bytes, every character on your keyboard has a representation in a byte for what that character is. And if you put a bunch of them together, then they make, to us, they make words. But to the computer, they're just a bunch of bytes with values in them. But there are some conventions, like with the floating point numbers and the complex numbers, there's some conventions. For example, if you have a string with the word dog in it, it's actually going to be 4 bytes long. Well, wait, D-O-G, but you have a 4th byte for the termination character. So 0, 0 in a string marks the end of the string. Okay. Sometimes. Okay, one of the things in Windows or, you know, operating systems in general that was a problem early on is that programmers wrote these systems optimistically. And when you have a chunk of memory, like if you're going to declare a field in your program that's you're intending for this variable to store last names, okay, for a simple example, how many bytes do you need to make that variable? 10? I mean, I'm sure we could all come up with last names that are longer than 10 characters, so we just truncate them. Does anybody still get mail, you know, envelopes with the names and stuff printed on there, where you see it in all caps and truncated after a certain point, if you have a long last name? Well, that's where that comes from. In the old days, the computers, they didn't want to take the extra storage to store uppercase and lowercase letters, so they only stored the uppercase ones. And they didn't want to use too many bytes to store the value. So they just chopped it to 10 and truncated it or something, 10, 12, whatever they decided. So that's where all that came from. When you see these big mainframes printing out a bunch of data, and it was all caps, yelling at us, as we would say today, and it was only a fixed length. Well, then we got smarter. We said, well, we've got more memory. Memory's cheaper. We're going to have much more memory available. Maybe we'll declare the last name field to be 256 characters. Nobody would ever have one that big. Well, the problem is now Jones as a last name only occupies the first 5 plus one more for the 00 for the terminating character. So 6 bytes you're using of this 256 byte field. What do you do with the rest of them? What's in the rest of them? Well, that was a real problem because hackers figured out ways that they could put a bunch of stuff in there and use that data using various tricks and things like that. If you start learning about tricks like SQL injection and buffer overruns and things like that, you can maybe learn the details. But the point is, there's a bunch of unused data, and it was very efficient to allow all that extra space. And at a certain point in history, we cared. Now we don't care as much because we have, oodles and oodles of memory, and storage space is cheap, and it's not as big of an issue. But back in the day, it was. So circling back to this, it's just important to know that in memory, in the bytes underneath these values that we're inputting, there are bytes in memory that hold these characters. And at the end of the string, often there's a 00 saying that that's the end of the string. So that's how strings are stored in memory. And if you take 2 strings like that, first name and last name, and they're both stored in different places in memory with a 0 at the end of them, and you want to create a new variable that contains last name, comma, space, first name, then you've got to perform an operation, a new spot in memory. You copy the last name there. You copy a comma space at the end of it. So you go through there and you find the 00, put a comma and a space with a new 00 at the end of that. And then you take the first name and you put it at the end of that. Now you've got one big string of characters with a 00 terminating at the end of it. Now you've got your last name, comma, space, first name. So all those operations that handle strings, they all are written to assume that a string is a string of characters, you got an array of characters in memory with a terminator at the end of it. Okay, so the next thing about this is formatting. So when you start combining strings and numeric data types together, you get those format codes. Now in the modules, in module 4, there's this PDF file, and it has a list of all of these. And you can get these from W3 schools also. It's not a secret handshake that we tell each other. But if you want to print things in a specific way, you can use these format codes to format it the way you want it to. So if I have a variable that contains this data in it, this floating point number of 3.1415926, and I format it in a print statement and I use this format code, then the output is going to just be 3.14, because we look at this and the .2 means I only want 2 numbers after the decimal point, and F means that it's going to be a floating point. So format a float with 2 decimal places is what that says. Okay, it doesn't say anything in front of there. Like, what if I said 2.2F? And that would be saying that I want 2 in front of the decimal and 2 in the back of the decimal. So it would leave that much space. So you can get really creative with how you want to format your outputs. And what we're doing is we're taking numeric data types from chapter 4, and we're combining them with string data types from chapter 5. And we're using the print statement to put the numbers into the strings in ways that we want them formatted. And, in the old days, before we had cool format codes like this, programmers would have to format this stuff manually. You'd have to write lots and lots of lines of code to do this. So it's actually nice and very convenient that we have these format codes available to let us just do it simply without even thinking about it. Somebody else has already solved that problem, and we're going to stand on top of their work to do it. Here's a good example. 0.0f means I just want the integer portion of this. But if you look at that, why does this say 2.7? And when I use this format code, it changes it to 3. Because you have to worry about the rounding, right? So when Python converts this, it rounds it. Python was specifically written to do that. Other languages don't. So it's a difference you need to know about. So when we get to cases where I'm trying to explain to you in general how programming works so that you can be successful when you go on from here, you need to just realize that Python does this and other languages don't. They'll just truncate it. So you have to understand the rounding rules. And if you've had a math class in the last 10 years, you probably already understand anything over 2.5 is going to turn into 3. Anything 2.49999 and below is going to go to 2. So it's not too high powered. Padding is cool. I mean, padding simply means using extra spaces to line things up the way you want them. The comma is a nifty one. In English, we use comma separators every 3 digits as our convention. In other languages, they don't. They use periods for the separators, and so you can format it like that too. Percentages are kind of fun. The exponents, I think we talked about the exponent stuff last time, right? But if you want to take just a plain old integer and you want to format it as integer, as exponent notation, then you can do that too in your print statements. You don't have to write the logic yourself. And then the right, left, center aligned is kind of cool. I have actually written, I don't know how many programs where I had to calculate the length of a string and the space that I wanted to go in and divide it by 2 and calculate the number of spaces that I had to print before I printed my string so that it would be centered. And now I don't have to do that, right? Python just does it for me. So this is what we would call a reference material. If you are, planning on going ahead and doing more programming in the future, especially in Python, then you might want to save this someplace and refer to it later. Because as you're trying to do assignments in here or writing programs commercially or, on your own, you'll want to refer back to these. There are many things like this where programmers don't remember all this stuff. They don't memorize it. We just look it up when we need it or look at examples of code. Instead of even looking it up, I would probably just open an existing program that I already wrote before, and I would Control F and look for print statements. It's like, okay, where is it? I know I've got it in here somewhere. Oh, there's the example of how to do it, and program by example. So that's real big too. But I just wanted to point that out, that as you're doing your assignments, as you're reading the book, and I think one of the assignments may reference this file to be helpful, but format codes. Let's see, I wanted to do some of those for you. Yeah, there's a good one. Okay, let's go to command prompt. So here's our trusty Python. And if I say print 5, I get 5. If I say print open curly brace, colon, dot to F, five. Oh. Let me see if this works. I'm just kind of playing. Where's Thank you. Okay, so there was a really simple example that I made much harder than it should have been. Thank you for the reminder. So if I say print, so the F is short, I believe, for txt.format. I think it's the same string. 5 is just a value. Like I could say x equals 5 and print txt.format x colon dot to F. What did I do wrong? Oh, that's what I forgot the other parenthesis. txt.format. Oh, it's a string.format. Okay. I don't know if it's me or the keyboard. There we go. Whew. So that's another way you can do it. You can take a string and say dot format, and the variable you want or the value, like I could have just said 12 also, and I get 12.00. Can you guys see that, or do I need to make it a little bigger? Okay, so now you can go back to that PDF file, and here's the format code from the PDF file. And here's the piece of data that they have in the first column, you know, the number. And then this is the output column, what you would see on the right. Another thing I wanted to point out to you is there's this this thing called math. Well, duh. But in Python, there's this keyword called math. If I say print math.py, import math. So if I say print math.py, then I get pi, right? There's also math.e, just a bunch of those normal mathematical constants that you like to use a lot. They're in that math thing. So you just import math, and then you have access to them. And you can look up on W3 Schools what those are. No, Python. That's not the math I was looking for. There's a math that has a bunch of, yeah, I want this. I want the, see, they list this one, but I wanted a list of all the others. Math module reference. Oh, here we are. So that lists all the functions that you've got, but here it is. Math.infinity, math.not a number, and then math.tau. Anybody know what tau is, what that constant is? I at least know what pi is. E, sort of, kind of, but I don't remember what tau is. You have to look it up. Anyway, if you need it. So this was an interesting one, math.infinity. So how do we represent infinity in a bunch of bytes? You know, because if you set that, if you say x equals math.infinity, well, what's x plus 1? Yeah, so there's an implementation of it, just like there is for complex, right? If you define a complex number and you say x plus 1, there's an implementation for that. I would guess x plus 1 would still be infinity, right? But anyway, they're there. They're used by certain people. If they're useful to you, use them. Otherwise, just file it away as trivia. Anyway, math.pi is an interesting one because we can say things like, where's my example up here? So I can plug that into my little example here and I get 3.14, just like they did in the PDF file, right? And so you can probably imagine how devious we can get with this now that you've got access to it. We can make all kinds of programming assignments where we say, oh, and by the way, the dollar amounts have to be formatted correctly. You can't have 8 decimal points, 8 digits after the decimal point, because if it's a dollar value, we're going to use a convention of two places after the decimal, stuff like that. Or I want to see the headings lined up and centered and that sort of thing. Yeah.
So the that you showed numbers that
Yeah. So this says it's a format code. I mean, all of this stuff is positional. So colon, .2f, and this is just the syntax you have to use. There are lots of variations of this. Like I said, refer to that PDF and you'll see a bunch of them. But yeah, this specifically says if there's I want to always print this with a decimal point and 2 digits after the decimal point, even if they're 0. Right? Remember our example from up here. X was equal to 5, but we still printed 2 zeros after the decimal because the format code says so. Yeah, and as you might imagine, if I say 5F, then I'm going to print 5 numbers after the decimal. So it's very powerful and interesting, and I could stand up here and show you 100 different examples, but awesome. Yeah, very cool.
And also, a program that said that the find the biggest number, like find the smallest number,
See, this is kind of scary. How many digits does it know pi to? Okay, maybe I hit the end. So it knows pi out to that many decimals, and then it zeros after that. Let me consult my cheat sheet again. Oh, okay. Here's another thing about Python that's kind of unique. Let me close this and start a new one. Okay, if I say print 5, I get a 5. If I say print 5 divided by 3, I get a decimal. Why? What's going on there? Okay, so something's going on, right? Because I got different stuff. We can go back to last week and do the type thing. Okay, 5 is an integer. But 5 divided by 3 is a float. So it's important to understand what's happening there. When we get into Python stuff, and last time we talked about how math is different than programming. In math, you have equations, and in programming, you have assignment statements. We don't have equations, we have assignment statements. So when you see an equal sign, it's always going to be on the left is the name of a variable, and on the right is always going to be an expression. Okay, and that's the important bit to understand. 5 plus 4 divided by 3 minus 17. And then I can print x, and I get a value. But this whole thing, no matter how many terms, how complicated that thing gets, it's an expression. And so another fun thing about these compiler construction classes, you can have big messes on your hands trying to figure out how to get the computer to understand how to evaluate expressions. It's very complicated, or can be. So especially when you start adding parentheses. So like when I say 5 plus 4 divided by 3 minus 17, am I going left to right? There's something going on there. Like if I say x equals 5 plus 4, oh shoot, I get 9. If I say x equals 5 plus 4 divided by 3, I should get 3, right? Because 9 divided by 3 is 3? Right, I did not get 3. Yes, exactly. Yes, exactly. There's a precedence to the order of operations here. We call that operator precedence rules. And so in order to evaluate an expression, you have to understand what the precedence rules are. And that's exactly right. We always put times and divide before plus and minus in math also. I don't have to say the parentheses, but that's exactly the same as parentheses 4 divided by 3. Right? That's what's going on there. So the computer knows the rules, the computer follows the rules. And if we want to understand what's going to happen with our code, we have to understand those rules too. So there I got the same thing, but if I say x equals parentheses 5 plus 4 divided by 3, now I get my 3.0. So there's a lot going on there. And so you just have to understand that's an expression. The expression is getting evaluated. And like we learned with the divided by, when you have those operations like the divided by default, it returns a float. It returns a decimal number. So the types get changed. The output of a division operation is a floating point number, not an integer. Even if both of the inputs to it were integers, the output is a float. So we just got to understand that that's what's going on in there. Okay. We've already done this, but there are functions that we've been calling. Like if I want to get the square root of something, I think I have to say math dot square root of 9. What is it? SQR. What is it? Yeah. Oh, I closed my command prompt. Yeah. So every time you start a new program or you start a new command prompt, you have to import math again. X equals math dot sqrt of 9. Print X. I get 3.0. So a couple of things now you know is that the math square root function you do like this, and you also know that the output of the square root function is a float because I got 3.0, not 3. Just like with the division operation. And I'll even make it more interesting. If I say math dot square root of 5 plus 4 divided by 3, even inside the parentheses, this expression is still going to get evaluated according to those rules of operator precedence, and the division is going to come first before the plus does. Okay, let's see if our handy W3 schools has something to help us out there. Python operators. Yeah, so here is a list of the arithmetic operators: plus, minus, times, divide, percent. Oh, that's not percent, is it? Modulus. So anybody know what the modulus is a fancy name for? Bing, bing, bing. Yes, it's a remainder. So if I divide X by Y, I don't want the result, I want the remainder.
Oh, I remember.
So 5 modulus 4 would not be 1 point something something. It would be 1, because that's a remainder of dividing 5 by 4. So it's pretty cool, and surprisingly, there's a lot of places where you need to know what the remainder is.
Oh, remember when you divide the number?
Yes, yes. Exponents. So it's the opposite of the square root, right? If I times 2. So if I say square root of 5 times 2, it's going to be 5, because 5 squared, the square root of that's 5, right? So fun stuff. I thought that there was going to be an operator precedence thing here. There we go. Operator precedence. So this is a nifty little unit to read through. I'm sure the book talks about this too, but shows almost the exact same kind of examples that I was showing. Just showing you that multiply and divide come before the plus and minus. Here we go. Here's my table. So Parentheses are always evaluated first. You always do pay attention to those first. Then exponents. Then the sign. That's an interesting thing too. Yeah, I don't know if I want to blow your mind with the whole bitwise stuff yet. We'll save that for later. But you get the point. You can go through here. Here's little old addition and subtraction buried in the middle, like a 4th round draft pick. They're just kind of tucked away inside all these other operators. So poor little guys. Anyway, that's a good introduction to that, hopefully. I want to point this out, not because I can demonstrate what's going on here, but because I can't. There's this feature in Python, like normally if I say x equals 5, and I look at the type of x, it's an int, right? And then I say x equals x divided by 3, what's the type of x going to be? Float. Okay, that's a little different than other languages because, for example, in C++, the result of the operation would be dependent on what the type of the variable is. So once x becomes an int, it stays an int. And if I said x divided by 3, it would truncate it and only put the result back into an integer. So in C++, if I did an operation like this, it would be float. And I may have mentioned this last class, but there's this thing called type coercion, where in some languages, it takes, you're taking a float, a decimal number, and you're assigning it into an integer variable, the coercion happens and it coerces it into an int. In Python, it doesn't. The result is smart. It knows that, oh, you don't want to lose that data. You probably want the result to become a float. So that's what happens. So even though I can't show you what to be careful of because Python's smart enough to kind of take care of you and protect you from losing data, I wanted you to know that that's going on there, to be aware of what the types of these variables are. Yeah.
So the program that reads x as a float,
What?
the x, does that read as a float? That's why
It's the x over 3. When it evaluates that expression, because we use the divided by, the result of that expression is a float. And so what gets stored into x is not an integer anymore. It becomes a float.
so if you were to do x times 3, what would it be?
Like x equals x times 3, or do you want me to start over with an int?
No, like, yeah, like the same thing as we talked times 3.
Okay, so x equals 5. The type of x goes back to an int,
Yeah.
right? X equals x times 3. So what do you think it's going to be? Is it going to be a float or an int? Int. And that's because the multiplication operation, you could never lose data. Yeah. So I just wanted to point that out. If it starts talking about type coercion, that's what it's talking about, is it's taking data of one type and converting it smartly back into another. And you've already kind of done this. When we say x equals int of input right? If I do that and I type 5.4, it says you can't do that because it's decimal and you told me to convert it to an int, right? But if I follow the rules and I enter 67. Yeah, it's an int, right? So you've already been working with this a little bit in order to get numbers from these input statements. I just wanted to point out what it is because it's a terminology thing that you'll see in the book. Math library, we talked about. Oh, here's one other thing that somebody pointed out to me. I don't know how I made it this far without knowing about this. There's this website called typing.io. Has anybody heard of that before? It's pretty cool. You can just try out the demo, or you can sign in and do more cool stuff. But just trying out the demo, there's one of these things for Python. If I click on it, so when you get in here, you're supposed to just type what you see. So CLAS. Okay, you get the point, right? You type what you see there, and when you get done and you type the last character, it stops and it reports, here's your typing speed, and here's how many unproductive characters you type, like the backspace key. One of the problems with traditional typing tutors is that they typically teach you how to find all of the alphabetic characters, but not so many of the special characters. And in programming, we use a lot of those special characters. And one of the biggest boosts to productivity in my career, surprisingly, I know, but it happened when I learned to type without looking at my fingers. Okay. I probably doubled my productivity when that happened. And it was because I went and took a keyboarding class. I don't even know if they have things like that anymore. FSW offers one. But they would sit you down with, programs and make you type as fast as you could and get better at these techniques. And they had special exercises you could do to get faster. And I think I got up to like maybe 52 words a minute or something typing English characters. But this is the first time I've seen one that was dedicated to programmers and helping us practice getting our speed up on writing actual program code in the language that we are intending to practice. So anyway, throw that on your when you're board list. And I would encourage everybody to try to spend a semester dedicated to trying to improve your ability to type software, or even your English stuff in Word without looking at your fingers, because it will definitely make a difference. More than taking a class on Python, it will help you be a more productive programmer if you're able to type without looking at your fingers. I know it's a small thing, but I wanted to point that out. Okay, so there's another assignment out there in Canvas. It's along the lines of the same kind of stuff that we've been doing. Hopefully that'll help you to practice the formatting stuff, and that formatting.pdf file is out there. And then I'm going to try to, we've been kind of languishing on these topics, chapters 3, 4, and 5 for a couple of weeks now. I'm going to try to cut that off and move into the conditional statement chapter 6 for next time. So hopefully that's exciting. We can get away from these simple, less interesting type programs. We can do some actual logic, and the bonus round where the scores will really change. Any questions?